Afternoon, Physics 20. I hope you guys are all doing well today. Today, we are going to look at the second part of our two-dimensional forces, and this is where we're going to be having three forces on a stationary object. Okay. So we have a field trip for this part of the lesson too. We will have another video after this one. We'll be looking at a rigging handbook that is my husband's. And as you guys know, he operates heavy equipment. And one of the things he has to do is lift heavy object with a loader that its tires are taller than I am. It's insane. So because he's going to be lifting heavy objects, and sometimes he'll be using slings with those, they need to do is actually all this physics here is something that he either A, does or uses the formulas in his manual, which are based off of this physics here. So I'll show you a little bit more about how that works, so a practical application of what we're going to be doing today in the next video. Okay, so for this piece here, we are going to be looking at... this thing does not want to cooperate. There we go. Okay, so we're going to be looking at three forces, and we're going to be having these act on a stationary object. So objects that aren't moving. These would be signs hanging from a pole. This could be a huge F-150 engine sitting on a massive pallet that is being lifted by a loader, and the loader is just kind of holding on to it. So this is where you're going to be doing a lot of things. We're going to be looking at a lot of tension and ropes, that kind of thing. And in this case, what you're going to know is you are going to be given, for these questions, one angle, and you're going to be given one force. And we are then going to be using a modified method to solve these types of problems, and these 2D problems. So your steps, ladies and gentlemen, number one, you're going to redraw all of the forces, okay? And tip to tail method to form a right angle triangle, okay? Now, because it's a stationary object, it's not moving, it's just hanging there, okay? The net force is going to be zero. Remember, objects that aren't accelerating, so therefore, including stationary objects, they have a net force of zero. Okay, so that means our triangle is going to start and end at the same point. Okay, it's going to start and end at the same point. So because our forces are going to add up to zeros, the forces aren't really going anywhere. All right, so the best way to look at how to do this is jump into the deep end. Okay, so let's scroll down. So here we have an object that's hanging from a wire, and it's as indicated in the diagram. And we're going to find the magnitude of tension in each wire. So remember, ladies and gentlemen, that tension, or T, is equal to the force applied. Now, that force applied is the force that cable is going to be applying to this object. Okay. So we have an angle which is here between the parallel here at the top, which is 70 degrees. And we have the mass of an object. So it could be a 37 kilogram sign. So we need to draw our vector arrows. That's the very, very first thing we got to do, is we need to build our free body diagram onto this guy. So let's think for a moment. What forces are acting on this? Well, first of all, I really hope you guys all got that our force of gravity is going to be acting on this guy. We also have our tension. I'm going to label this as T1 on this guy. And we have tension, so T2 there. Okay. So remember that because this object isn't accelerating, it's going to have an F net of 0. So when we redraw our vector arrows, we're all going to have our arrows coming back to that same point. Okay. So they're going to be essentially going around and around and around. Remember how previously when we did our vector diagrams, we would have something like this, and then your resultant is like that, where we have the two arrows crammed there, and then our theta's here. As we're starting here and ending here. So we are going to have a resultant pointing towards this other arrow here. That's not what we're going to be seeing in this case. Okay, this is going to be the only time I want to see your vector arrows going in a circle. Okay, so essentially what I'm going to do is it's going to be as if I am dragging my vector arrows when I redraw them. We have to try and keep kind of a ballpark of the same angle, and we have to draw them tip to tail. So I'm going to take my T1 here, and I'm going to just redraw it like that. Okay, so I've taken this arrow and I've just dragged it over there essentially. Well, now I have FG, that's an easy one. FG is going to go kind of like that. Okay, so I've taken this vector arrow and I've dragged it over here. Remembering my vectors have to be tip to tail, so that means I've got this arrow here, that arrow there. These two are still tip to tail. Now I've got this third arrow to deal with. I'm going to take this one, I'm going to label this guy as FG, and then I'm going to take this tension line and I'm going to drag it down here. That's going to form T2. So notice I now have a right triangle. That's going to be my right arrow, right angle, excuse me. And all of my vectors are now aligned tip to tail. That is the key. So notice this is the one case where I want all of my forces canceling out. Okay, they all cancel out. We're not going anywhere. Okay, tip to tail, tip to tail, tip to tail. We're not going anywhere. Okay, so our next piece is we're going to need to determine our theta. Okay, we need to determine our theta. Now, 70 degrees, ladies and gentlemen, notice the location of the 70 degrees. Is it inside the triangle, or is it between T1 and the horizontal? It is between T1 and the horizontal. I'm just going to grab my eraser here, and I'm going to move that T1 a bit. There we go. So the theta on the outside here is 70 degrees. Okay, we're going to give that guy the name red theta, like we do in class. And I am then going to give this theta here, the one that we actually need, that one is going to be blue theta. Okay, same just thing like we do in class, red theta, blue theta. Okay, so this blue theta, that is the angle that we are actually going to be needing here. So ladies and gentlemen, what is the value of blue theta, and how do I find blue theta? If, ladies and gentlemen, you said subtract from 90 degrees, you are 100% correct. So you're going to subtract 90 from your 70 degrees, and you're going to get a value of 20 degrees for blue theta. Okay. Back to red. Okay. So that is the theta we're going to be needing here. Excuse me. Okay. So our next piece is we are going to need to figure out the tension on each cable. So we need T2 and we need the value of T1. Well, we've got a problem. We have the mass of this thing, but we don't have anything else. Or do we? Can you guys come up with a solution? If you said we can go to calculate FG, well, FG is equal to mg. We've got the mass. Mass is 37 kilograms. So ladies and gentlemen, I'm going to calculate my mg, so my 37 kilograms, and I'm going to multiply that by my 9.81, and that's going to give me my value of Fg, which is going to be 362.97 newtons. Okay, so that's my Fg. Okay, so 362. Okay. So think for a moment, ladies and gentlemen, how am I going to get my T1 and T2? Good, trig. So you're going to use trig for this now. The tricky thing as well with this type of question is I want you to be very, very careful with looking at your triangles. Remember, our triangle, look at the orientation of them. What is our hypotenuse? T1, T2, FG? FG. Your hypotenuse. Now, we know this because it is directly across from our 90-degree angle here. So be very, very careful for that. In this type of question, it's often this guy who's going to be your hypotenuse. Our right angle triangle is going to be canted a bit. Okay. So in order to find T1, okay, which I'll find T1 first because I can, I have my hypotenuse, and then I have the side that is adjacent to this. So using your trig, you're going to determine that you want cosine. So T1, okay, we'll write this a bit differently. There you go. So T sine is going to be cosine of 20, and we are going to find T1, which is the adjacent, and over our hypotenuse, and FG is our hypotenuse. Okay, so I'm going to multiply both sides by FG here, and that's going to cancel. And then we have my T1 is going to equal my FG cosine 20 and FG, so 362.97 dot 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 times cosine of 20. So ladies and gentlemen, don't forget to make sure your calculator is in degrees and not radians, because we don't want to have a rad time while doing trig. Yeah. Please laugh at my puns, guys. I really hope you're laughing at them. Sitting here all alone at home, making puns to myself at the computer. Someone better be laughing at least. So our value of T1, ladies and gentlemen, is going to be your 341.08 dot 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 newtons. And with sig digs, I want 3. So we're going to round this one to 341 newtons. Okay. All right. And keep in mind as well, ladies and gentlemen, the question does say magnitude of the tension. So that means I do not want direction with these guys. Okay. Let's find T2. Let's actually rewrite this a bit nicer here. There you go. So in order to find T2, I'm going to come back and look at my triangle here. And while looking at my triangle, while T2 is here, T2 is opposite of the 20 degrees. So that means I'm going to use sine because I have FG, which is the hypotenuse. Now, you could argue that, yes, you could now use Pythagorean theorem. Yes, you could use tangent. However, I'm not going to. Why am I going to use sine and not any of my other trig options? Right, because my sine is still going to have the least amount of math done on it. The only value I will have calculated is going to be FG. Everything else is given. Whereas the second, if I use Pythagorean theorem or tangent, the values I'm going to be using will have had other calculations done on them. So it's going to increase my error rate, which I want to avoid. So my sine of 20 is going to equal my T2 over my hypotenuse, which is my FG. So I'm going to multiply both sides by my FG. And then my T2 is going to equal FG sine of 20. And my FG is 362.97 dot 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 times sine of 20. I'm going to move this up so I don't write on my face. And have I ever walked into class with pen on my face before? I'm pretty sure I have. If it's not your class, I've definitely done it in other classes before. I can't technically write on my face here, though. Okay, so once you put that in your calculator, you're going to wind up with 124.14 ... newtons. And we're going to round this to our 3 sig digs, so 124 newtons. All right, and there you go. Okay, so ladies and gentlemen, I hope you guys found that all right. So what you guys can do some of these practice problems here, and then do this practice problem here. And that is the end of this section of notes. So ladies and gentlemen, hope you guys enjoyed that, and stay out of trouble. Have a good day. See you all later. No fires, injuries, or explosions. Now I can't turn this thing off again. There we go.